Hello, everyone. If you can hear me, please type something in the chat window. Hello, everyone. Oops, there's an echo. If you can hear me, please type. Test one more time. Okay, cool. Hello, Stefan and Anton. I hope I pronounced the names right. So there was an echo. Is it better now? The echo is gone and you guys still can hear me? Okay, cool. Excellent. Alrighty, so it's time to start. Welcome to our first online evolutionary robotics meetup. And today we are going to discuss a hybrid evolutionary designer of modular robots. But first, let's do some announcements. So we are calling for proposals. We want to hear from you. So please contact us if you would like to talk about a project, research paper, or just anything cool you like to share that is related to evolutionary robotics or robotics in general. We need you and we want to have you involved. So please, let's do it together. Our agenda for today will cover an introduction. Then we are going to discuss modular architecture, then evolution in general, and evolution in regards to this proposed system, and some experiments we've done in order to test the proposed system. And then finally, we're going to conclude and have a Q&A session. So let's start. The majority of robotic systems usually consist of two parts, the morphology and the control. The morphology, as most of you know, refers to the physical structure, the hardware or the body of the system, while the control refers to what? I want to hear from you. Please use the chat window. The morphology is the body and the control is what? I'll wait for like 10 seconds and then we'll move on and give the answer. All right, I guess I'm going to give the answer then. The control is the brain of the system. The brain that governs the body of the robot. Those two parts, the body and the brain of the robot, contribute to the overall behavior of the system, and both of them are affected by the environmental changes, the environment that surrounds the robot. Usually, designing a robotic system for accomplishing a specific task starts with designing the body of the robot and its behavior. And then after designing the body of the robot, the design of the robot's control takes place without considering the fact that body, brain, and environment are highly interdependent. That's why evolutionary algorithms are used to develop autonomous robots by exploiting the relationship between the control and the morphology of the robots along with the surrounding environment. Our proposed method, the evolutionary method, allows co-evolving of the robot's morphology and control, the brain and the body of the robot simultaneously in the same time in a specific environment. And it takes into consideration also the environmental changes to produce the best adaptation behavior. In our proposed system, both morphology and control are co-evolved during runtime, using real hardware to continuously produce new feasible robots. We are going to describe the hardware that we use in the next slide, which is kind of different than other systems that use some simulation environments without considering any physical limitations. Our proposed robots are developed by evolving predefined parts that make up a subset of the existing robotic modules and raw materials in the environment. So the resulting set of robots can have diverse morphologies and locomotion methods accordingly to best fulfill the task at hand and face environmental changes. And since behavioral physical systems are more difficult to design than not situated and disembodied computer programs due to their dynamic and unpredictable properties, we propose a hybrid genetic programming and genetic algorithm approach to address the challenges of co-evolving the robot's control and morphology. So let's move on to the next slide, which will discuss the modular architecture and the hardware that we use in our research. So modular robotics are composed of multiple building blocks of a relatively small repertoire. As you can see here, we have only 6 cubes. Each of these cubes has uniform docking interface that allow transfer of mechanical forces and moments, electrical power, and communications throughout the robot. The modular building blocks often consist of some primary structural actuated units and potentially some additional specialized units such as grippers, feet, wheels, cameras, payload and energy storage, and generation units. Modular robots have become of great interest these days because economic mass production of units is easier using modular robots. The degradation of function when damaged is better with modular robots. And the capability of transitioning into topologies suitable to the task at hand is also easier using modular robotics. More benefits include the ability to self-assemble, which is organizing a multi-unit system from a collection of independent units, and self-reconfiguration, which is the ability to transition from one topology to another using a series of attachments and detachments. Also, self-repair, which is a special type of self-reconfiguration, which allows a robot to replace damaged units with fresh and working ones, or to reconfigure into a different shape that can work in order to complete the task at hand and maintain availability. One last benefit is self-reproduction, which is the ultimate form of self-repair that allows the robots to reproduce themselves. The kit that you can use in this slide is called Cubelets, which is a modular robotic construction kit that allows building autonomous robotic systems. Cubelets consist of small cubic building blocks that connect via magnets and unisex connector. These connectors allow information and energy to flow between the modules. As you can see, each cublet implements a specific function. For example, the first one is for driving. You can see the 2 small wheels. It will allow this cube to move. The second one has a flashlight that can be used as an alert system, for example. The one in the middle, in the second row, is a battery. And you have to include this cube, the battery cube, in every robot that you design, because this gives the information to the other cubes. And one other robot is the distance, which is an ultrasonic sensor that can use an input tool in a robot. So let's talk about evolution now. A behavior-based evolutionary approach is used to build the autonomous robot by co-evolving the control and morphology, where each individual in our system is treated as a pair of brain and body. Again, the brain is the control and the body is the morphology, in which a brain represents the control, again, and the body is representing the morphology. The brain is represented by a pars tree structure, as you can see it, to express the genotype of the robot, while the body, or the morphology, is represented by a string of real numbers. Each number represents a determining structural element in the robot that affects the behavior of the robot. So since each robotic part is represented separately, the brain is represented in a different way than how the body is represented, we are using different techniques to evolve these parts individually. So the brain is evolved using genetic programming, and the body is evolved using genetic algorithms part. Before talking about evolving control and evolving morphology, we need to mention that the initial set of robots is created at random, with each individual has its own unique values, has its own unique brain and body value combinations. The evaluation process is carried out by executing in simulation a brain on a corresponding body and measure the fitness of this combination in a certain environment. Then after evaluating each individual to select the fittest, genetic operations such as crossover, reproduction, and mutation are applied to the individuals that are probabilistically selected from the current population to create a new offspring. While the reproduction copies the selected parents into the next generation without changing any values for the controllers or the bodies, the crossover and mutation can change either the brains or the bodies, but not both, in order to maintain the structure accuracy. Evolving control. The robot control, or brain, is represented, as we mentioned earlier, by a pars tree structure, which captures the executional ordering of the functional components within a program, such that a program output appears at the root node, functions are internal tree nodes, a function's arguments are given by its child nodes, and terminal arguments are found at leaf nodes. As most of you know, a pars tree is a particularly natural structure for representing programs in Lisp, which is a language used for genetic programming. Our control is considered as a combinational logical system where the output values are determined by the input values at a certain point of time. So the sensor readings can be mapped into output commands or motor commands. This combinational logical system is divided into a Boolean tree. And in order to improve the fitness, subtree crossover, as you can see in the figure, and point mutation operators are used. Subtree crossover exchanges randomly selected subtrees between programs. But this operation should be restricted, such that the level of the selected crossover point in the first parent should match the level of the crossover point in the second parent in order to prevent meaningless results. Point mutation randomly changes the functions or leaves found at a proportion of the node within the parse tree. The number of nodes to be mutated is determined, which we choose to be 1%. Evolving morphology. So the body or the morphology of the robot is expressed by a string of real numbers, each representing a robotic structural feature depending on its position in the string. So, genetic algorithm is used to evolve the morphology and solve our optimization problem. We use here single point crossover, which yield the results in a number of comparative studies similar to our research. And we use random mutation techniques to create new morphologies. As you see in the figure, single point crossover method allows each pair of body strings to undergo crossover as follows. A single number in a randomly selected position, which is k, for example, number 3, k equals to 3 in our first example, is selected uniformly at random, and then the two new body strings are created by swapping all the numbers between positions k plus 1, which is 4, until the end of the string. In order to maintain diversity in the search space, we applied random mutation to each offspring in the population with a predetermined probability. So we did some experiments using benchmark robotic problems to demonstrate the quality of the robots designed by this proposed system. The problem was a linear mission that involves moving the maximum possible distance on a flat surface. And since the objective is to move forward as far as possible, we defined the fitness function to just measure the distance, and we assigned a threshold distance. So if the robot succeeded to move that threshold distance, then we will consider the number of modules used. The maximum number of modules in our case is 6, of course, because we have only 6 cubes in the robotic kits that we used. Using the proposed designer, the 3 robots that you can see were designed. So I would like from you now to use the chat window. I can see some questions popping up. So I'm going to actually go through the questions at the end of the presentation. But for now, which one of these robots do you think achieved the best performance and gave us the best fitness level? A, B, or C? Oh. So I'll ask the question again. Which one of the three robots, A, B, or C, do you think gave the best fitness value? Anton said B. Okay. The question again. So the mission was for the robot to move the maximum distance value. Using the proposed method, it yields these three designs. One of these robots achieved the best fitness value. Which one do you think achieved the best fitness value? B? Okay, so both of our guests, Anton and Stefan, said B. Well, unfortunately, it's not B, it's C. Why? Because in the fitness value, I should actually share the fitness function, but I'm going to send it later in the email after the meetup. So the fitness function takes into consideration, oh, I'm sorry. I'm sorry, Stefan. It takes into consideration the number of modules. So the number of modules used in C is smaller than the number of modules used in B. Somewhat unexpected. Yeah, I agree with you, Anton. It's always like that when you do research. You expect something and the result is something different. All right, so we will conclude now. Still waiting to see the conclusion slide appear in the video. All right. So this paper presented, it's a research paper that will be actually available on IEEE probably in the next couple of months. So it presented the basic results obtained using our proposed evolutionary designer that is capable of automatically designing complete feasible robots. So it yields the design and we attach it by hand for now. But as a future work, we would like to include self-assembly capabilities in the robot. So the robot will self-assemble in order to result in the output design of this algorithm. And then it will start moving forward, for example, to achieve the task in hand. Like, for example, here, move a certain distance, or maybe paint a wall in another benchmark problem. Then after achieving that, we will start working on adding self-reconfiguration capabilities to the resulting robots. So that's it for now. If you have any questions, please feel free to ask them. Questions. Any? Oh yeah, please go ahead. Okay, so Stefan has a question. Do you know what limitations there might be with Cubelets? Processing, memory? Okay. Yeah, obviously the memory is a big limitation. The processing also is another dilemma because when you're using Cubelets, you gotta program each Cubelet separately. I'm gonna also send the links to Cubelet programming frameworks. So they have something called Cubelet Flash, if I'm not mistaken. Cubelet Flash, where you drag, no, I think Cubelet Flash has the C programming IDE, but the other product they have. I think it's called Blockly, if I'm not mistaken. This one has drag and drop features. Let me just, give me 1 second just to give the right names. All right, so I'm gonna go ahead and okay, here. Yes. So the link. All right, so I'm gonna go ahead. Oops. So here is the link that you can actually navigate to and see the two Cubelets programming environments. Yeah, Blockly, where you use drag and drop. This is actually tend to be for kids in order to teach them how to program. And the other product is Cubelets Flash. So this use C programming in order to program each Cubelet. Yeah, another limitation is that you need to include the battery Cubelet in each design. So this actually will add one cube or one module to every robot that you're designing. Where, for example, in our situation, I thought one ideal result will be using only the drive cube without attaching any other cubelets, because in this case we don't need any input, like we don't need the infrared actually reading infrared values for obstacle avoidance. So that's another limitation. How will do? I hope that answered the question, although I took longer than usual to collect the parts for the answer. How will do you designs transfer from simulation to reality? Yes, so these three designs were taken out of 300 designs. The framework yields some designs that can't be used. That's why, I added some parameters to the algorithm in order to result in some realistic results. I was also, again, we will talk about the hardware limitation. I was expecting something with minimal number of cubes, but because we have to use the battery module, it added more modules to the one that we're using. Like, for example, in C, I would have actually wished to see, oh my God, it's broken. Let me fix it here. Okay, in slide number C, in the robot number C, I don't know if you can see it. I'm trying to change it, but it takes some time. There is a delay where you can see it until it's reflected in the video. I don't want to have the ultrasonic sensor on top because I'm not doing any obstacle avoidance. So yeah, 3 out of 300. I think it's a small number, and I wish that we had better results, but we're in the phase of exploration, and hopefully we will have better results in the future. In particular, given a robot that travels, yeah, how likely it is to travel comparable distance after fabrication. Let's say 50% of that 10 systems in 10 centimeters, sorry, in simulation. Because when you attach the cubes together in order to fabricate or make the resulting robot, usually some of the robots will be heavy to move in comparison with the simulation. So it's not going to give you 100% same result in simulation. No, it's going to be like 50% or less. How does your approach differ from the existing related research? That's a great question. Some research methodologies focus on either evolving the brain or the body at one certain time. Some algorithms or some research methodologies co-evolve both the brain and the body at the same time using different algorithms. We tried here to use a combination of genetic programming and genetic algorithm in order to produce something that is different than what has been done in the research. And the results are encouraging so far. So that's what makes us different, is that number one, we're trying to co-evolve the brain and the body using a combination of GA and GP together. And we are trying to use modular robotics in order to implement physical robots. Perhaps the evolutionary. Yes. Anton added that standardizing the blocks can help with the reality gap. I totally agree with that. I wish each of these cube has its own battery and its own USB in order to program it immediately instead of actually using a Bluetooth cube that is not shown in the presentation. It will help. Yes, this will help in bridging the gap, the reality gap, and producing more feasible robots. I'm thinking also about other features that will make this research different than other research methodologies. Going back to Stefan's question, some of the features are not implemented in this current system, but they are mentioned as future work, which I mentioned in the conclusion slide, which is trying to use self-assembly. So instead of attaching the cubes by hand in order to manufacture or make the resulting robot, the robot can assemble itself, and then it can reconfigures itself in order to adapt to the environmental changes. So we're taking it slowly, one small step at a time. So any other questions before we conclude and finish the presentation? No, I think no more questions. So I would like to thank you for your listening. And again, if you have any cool research or any cool project that you're working on and would like to present, please feel free to reach out. Thanks again for your time and your contribution. And I'll see you back in 2 weeks.